Hi everyone, we'll be talking about convolutional neural networks today. I'm Dhruv Shah and Soham will be taking the next half of the recitation. So has anyone worked with convolutional neural networks here before? Okay, so one person has worked, right? So convolutional neural networks have shown state-of-the-art results, especially when it comes to images. And we'll be taking a small peek at it today. So first we need to understand convolution, how do we compute the convolution. So what convolution is that if you have an input and a small window, or this window is also known as a filter or a kernel. So if you have an image which is, I don't know, 224 cross 224, like a very large image, and you have a very small window, it can be 3 cross 3 or 5 cross 5. How do you slide that window across that image and gather really valuable information from that image? So that's what convolution does. So once you have some input, you overlay a small window which is also known as convolutional kernel on the input. So to extract the information, we use dot product. So the window, if it's 3 cross 3, then it is a set of 9 learnable weights. So that it's like a 3 cross 3 matrix, and each of that value is a weight which we are trying to learn. So we find the dot product between the kernel and the segment of the input that it is on, and then we slide the kernel, or more precisely, we convolve the kernel over the whole image and gather. Do dot product over each segment and collect information. So we keep on doing this until we have gone through until we have convolved over the entire image, and this is basically what convolutional neural networks do. They have a set of kernels to learn, and they'll convolve over images and try to extract valuable information. So if you for example, let's say you have a time series data. So as you can see that this is 3-dimensional because it has 3 rows, and what happens is in red what you have are the weights. So you have 1 or 0 here as weights. Usually the weights can be any real number, but here we have 1 and 0. So when it's striding over, as you can see, it will keep on learning. So the values that we are getting, 2, 3 and 4, they are getting by multiplying each weight and taking dot product. So has anyone seen these animations before, for CNNs? Okay, we have them in our presentation. So you can see, right? So 0 is multiplied by 1. If you take 0, 0, 1 and the weights are 1, 0, 1, so you get 2 there, because all the 3 time series, all the 3 dimensions, we multiply the whole matrix and then we add them to get 2. Then for the next stride, we take the dot product, add all the numbers and get 3. And for the third stride, we get 4. So that's how we are collecting information and sort of getting just finding a new representation for that whole time series. So that was like a 3D time series. What if you have an image but just with one channel? So if you have something like that, then the stride usually happens in 2 dimension. As you can see, it's going through all the possible up, down, as well as right, left. And the same thing happens. You have the input and the weights here are either 1 or 0, and you just the dot product happens. And as you can see, we have sort of downsampled, so we have collected extracted some meaningful information, so we have just compressed the size of what we want to learn. So this is how the convolved feature is being calculated. It's basically dot product between the kernel and the part of images. Now the images are usually 3 channels, right? So so this is now a little more complex, but it's the same thing again. You have an image. So let's say that this image is 3 channels. So one filter here will consist, if here our filter is 3 cross 3 size, right? But if we have 3 channels, then our filter will be 3 cross 3 cross 3. So we have total 3 filters. Each filter, as you see, for each segment of the image, you compute the dot product for each channel, and it will learn different weights for different kernels, and then it will add all of them and give you some output there in your convolved feature. Right? So you can take a look at this. This is what you are doing in your homework 2 part 1 when you're working with CFAR10 dataset. So once you have an image, the kernel will stride over all the possible, it will stride over all the possible regions. You can also, so here the stride is 1 because it's moving like, it is taking 1 step to the right, 1 step like down. But you can also have stride equals to 2 where it will like just jump 1 and like skip 1, or you can have stride equals to 2 where it will skip 2. Yeah.
So do you have a different filter for each channel?
Yes. So when I say that there is that a kernel, you have a 3 cross 3 kernel, then the number of weights to learn will be the number of input channels. So it will be, if your kernel is 3 cross 3 and you have 3 channels, then you'll have actually 3 kernels of 3 cross 3. That's actually one kernel here.
27 weights.
Yeah, 27 weights.
And then that's going into one
filter. Yeah. No, this is a filter.
Yeah, that entire cube is a filter, correct?
Exactly, yes. And that will give you one value. Like it will fill one cell. So these 3, when it has convolved over that specific region on the image, they'll give you like one value here.
Yes.
And when you say that you have 5 kernels, what it means that you have, if you say that you have 5 you're using 5 kernels, then you'll have 5 multiplied by like 3 kernels of each of size 3 cross 3. Yeah.
So I think the reason why I asked is in the paper for our all CNN implementation, it talks about that we have 3 cross 3 convolution through our 3 channels.
Okay.
But then it says that we have 96 filters. Is that equivalent to just saying we have 96 hidden nodes in that layer, like in a dense layer? But filters are now the nodes that were in our dense layer before are now filters in convolution layer. Are those equivalent statements?
The nodes, can you repeat the question lastly?
So the layer in our all CNN paper,
yeah,
it's just saying that there's a 3 by 3 convolution
yes,
with 96 filters,
okay,
and a ReLU activation.
Okay.
So is it appropriate to interpret that as a 3 by 3 kernel? The window is actually 3 by 3, and then when it says 96, we have 96 different weight combinations in that layer.
Yes, and so if the layer before that, we also need to consider how many channels are there in the input. So if it's the input, then there are 3 channels. So it will be 96 cross 3 cross 3 cross 3. So 3 cross 3, that is the kernel size. 3 is the input channel dimension, and then 96 filters you have. So that those are the number of weights you'll learn for. So how do we compute a convolution? So first question that we have is, does the kernel have to completely fit inside the input? So actually it does not. When you don't, so you can apply padding to it. So padding can be where you create a border of zeros around the input. If you don't have that, then the corner cases and the edge cases, they are not convolved as much as the inside, the cells which are inside. So once you apply the padding, then all the cells will get equal, will be convolved equally, and they all will be used same number of times. And the second variation that we can have is, do we have to place the kernel at all possible locations, or we can just place them at regular intervals? So that's stride. What in the previous example we showed that the stride here is 1 because we are we are just taking 1 step at a time. We can also take 2 steps at a time, but then that will reduce the complexity. because we'll be like learning less. So, but then we might skip over some like features learning, so that we have to decide whether we should like increase the stride or decrease the stride. So if we can see here, so this, so when you so here we'll explain so the green there, it is a filter, and the blue is your input. So when you have no padding and no stride, then then it's the same as what we have seen before. When you have padding, then as you can see that there are just some, like, we add information around, like we can add like zeros around our input, and all the input neuron will come equal number of times in our calculations. We can also have the second row and first thing, where we have strides, where we are skipping over one each time. So this is like the variations of convolution, of conv operations that we can do. So why are we using these convolutions, like what they are actually doing? So like we are sliding this input, but what intuition are we getting behind like just sliding this kernels over the input? So there are two things. The first is these kernels are trying to extract local features from the images. These local features can be edges or some blob of particular color. And once you have deep convolutional neural networks, they can extend to just like recognizing some kind of object in an image. And also convolutions, they are a good way to reduce model complexity compared to when you have a multi-layer perceptron. The number of parameters that you have to learn decreases drastically, which we'll show in the next slide. So first we'll talk about convolution as a feature detector. So like let's say that you have an image, and how do you find like edges in those images, and how do you find a combination of the edges, like some kind of shape in the image? That let's say that your weights are in this vertical order. Such convolutions, such filters can be used to find vertical edges in the image. And when you have like these horizontal numbers, like 1 to 1, 0, 0, 0, minus 1, minus 2, minus 1, you can use them to detect horizontal edges. And then you can use some kind of combination of like this horizontal edge intensity and vertical edge intensity to find different combinations of edges. So this will become clear in the next slides, as I'll show that once the first a convolutional neural network model will first try to learn like simple local features like edges and blobs, and then as it like progresses, it will try to learn more complex shapes. So as you can see, when you have an image, when a kernel that is like trying to learn vertical edge, when you try to visualize that, it will see, like you can see something like this. When you have a kernel which is trying to learn a horizontal edge, then the image that it's trying to learn, you can see it's like that. And when you have a combination of, let's say, any of these equation, like the second equation, horizontal edge intensity, and when you're trying to learn some combination, then it can look something like that. Or you can also see that when you same thing, when you're trying to learn horizontal edge, like what it looks like. So this means that the kernel has learned to detect horizontal edge. That means that it's trying to detect vertical edge, and that's like a 5x5 box of like horizontal and vertical edges. So a convolution is used to extract simple features in the local neighborhood of each position in the input. So for image, it will try to first detect edges, corners, dots. When we are using CNNs in text, convolutional neural network will first learn prepositions, short phrases, compound words, which occur like more times than the other words. And when you have sound intensity waveform, which you are working in the homework, like part 2s, it will first like learn to understand phonemes, tones, inflection. So CNNs perform convolutions on CNNs. Like when you say deep convolutional neural networks, they perform convolutions on convolutions with some nonlinear function in between to find larger and more complex features in the input. So once you have learned all the edges, corners, dots, how can you combine those to like actually detect some kind of shapes? So now let's talk about what convolution means for audio, which you're doing in part 2, right? So audio features, when using convolutional neural networks, we usually have MFCC features, which are 40 frequency band. That's the input dimension is 40. So why does it make, so CNNs are they give good results for images, right? Why does it make sense to use CNNs for audio? So that is because the CNNs are translation invariant. What translation invariant means is when CNN has understood or detected some feature at some location, if it detects that same feature at some other location in the sound or in image, let's say that it has learned that a CNN has learned to detect an edge in some in some part of the image. If that same edge comes in different part of the image, CNN will be able to understand it because that same kernel has we are striding it all over the image, and that's why it is translation invariant. Also, compared to multilayer perceptron, which you did in homework 1 part 2, CNNs have lower complexity in terms of number of parameters to learn, which I will explain now. Okay, so let's compare MLP and CNN for MFCC. Our input dimension in the frame is 40, and let our context window size be 10. So if we have one frame, we take 10 frames above, 10 frames below. So now our input dimension is 21, 40, correct? Okay, and our output is the number of phonemes that you had was 138. So if we use just like a 3-layer MLP with a hidden layer size of 128, then like can anyone like tell me what the number of weights to learn will be? Like how many number of parameters will we need to learn? Like not exact number, but like the calculation. You have 21, 40 as your input dimension. So when you flatten it, it will be 840. And then you have 3 hidden layers of 128. And then you have output like last layer with 138 possible categories.
So it'll be 840 by 128, 128 by 128, 128 by 128, and then 128 by 138.
Exactly. Right, so it's 840. So this is approximately 160,000 parameters. Now, if we use, let's say, now we use a 10-layer CNN, and this model is very basic, where we have like 3 filters, each of size 3 cross 3, and stride equals to 1, and we are not using any padding. So instead of a 3-layer multi-layer perceptron, now we have a 10-layer CNN. So here I'll show you like how many weights we'll need to learn. So the first input is it's just one channel, right? So and we have 3 cross 3 filters, so it will be 27 for the first. But now that the channels has increased to 3, will be instead of one channel here, we'll have 3 channels there. So the 10-layer perceptron with just the first like one fully connected layer at the end is like 100,000 parameters. And if you notice, the last fully connected layer is taking up all like most of the parameters. Like this is very low compared to that fully connected layer. So we yeah.
Can you explain the 1938 and 138?
Wait, it's 9 cross 38.
Okay.
Yeah. Sorry. Yeah, it's 9 cross. Actually, it's 9 cross. Wait. Give me one second. No, it's the so what this term, what it should mean is after you have gathered all after you get all your the output of the convolutional layer, we just stack it and then pass it through a fully connected layer. So the last layer is 138. I probably made some mistake in calculating this. So it will be 9 cross 3 cross 3 cross 3. So that's 3 3s are 9 3s are 20. Okay, 81 cross 9. Yes, so this will be 81 into 9 multiplied by 138. I'll just edit it. But the last layer is where all the weights are concentrated. Okay, so when in a typical convolutional neural network, you have convolution operation, then nonlinear operations that can be ReLU, sigmoid, tanh. You also have pooling. So what pooling is when you have learned some feature, then valuable information, they will have high values, so you can use max pooling to actually downsample your data. So what that means is, once you have, let's say that you have learned 64 channel feature, 64 channels of 224 cross 224, you can actually use max pooling to reduce the size of that to, let's say, 112 cross 112 cross 64. And if you see, this is still preserving the necessary information even after you have downsampled. And how downsampling occurs is, here also you have a stride. So let's say that you have this 4 cross 4 image and you have 2 cross 2 stride, and stride of 2, and your filter size is also 2 cross 2. Then you can just take those, you just need to, instead of doing dot product, you just need to perform max operation for max pooling along the whole image. When you're doing average pooling, you can use, instead of the max operation, you can perform average over there. So we can preserve both pieces of information pretty well with max pooling, and you reduce the amount of memory you need. So max pooling splits a feature map into fixed size pools and computes the maximum value within each pool. So if a feature is expressed strongly at some location in the input, then the output for the pool containing this location will also have a high value, because you have taken the max value in each stride. The pools are usually quite small, so we would still know fairly accurately where the features are located in the input. And as with ReLU, this max operation is also still differentiable. We'll do the it's the calculating derivative is similar to what we did in ReLU. And also we learn to be little more robust to translation. So if we move one pixel, if we change one pixel, we don't want the prediction to change, but because we have used max pooling, it is just noted down the max value from that, all the strides. So even if there are minor changes in the image, we don't need to, our predictions won't change. So it's a little more robust. Okay, now let's, yeah.
How does the max pooling, how is it affected by multiple channels? Or this doesn't, if we have 96 filters from the previous layer, we perform a max pooling step, we're still going to have 96.
Yes.
We're only doing the pooling on individual.
Yeah, on individual slices. Yeah, on each channel.
And then we still count the same number of channels.
Yeah, the number of channels, as you can see, the input is 224 cross 224 cross 64. It will still remain the same. So that's why we just showed you on one channel. On each channel, this operation will occur, and then the number of channels will remain the same when it comes to pooling. So now let's talk about what happens when we have a stride greater than 1. Stride means the number of steps we are taking when we are convolving over the image. So we can either take move to the next segment, or we can skip one and move to the next. So when you do that, when your stride is greater than 1, we reduce the dimension of the output and hence the complexity. but this comes at the cost of being more sloppy at determining whether a feature exists in an image, since a layer with stride larger than 1 might skip over the location where the feature is expressed more strongly. So there is a risk of that we are actually like missing out on some information which the model might not be able to capture. So fully connected layers. So we talked about convolutional operations, non-linearities, pooling. So the fourth thing that we usually have in a convolutional neural network is a fully connected layer, which usually comes at the end. We don't use fully connected layer in the beginning of the neural networks. We first like try to extract as much local information as possible by convolving over as much as possible, and then using those convolved features like try to do classification or whatever task that we have by using fully connected layers. So what we do is we simply treat the final feature map as a vector. So once we have all these, like let's say we have 4 feature maps here, then we just like flatten them out, concatenate them, and like consider them as like a simple vector, and then like perform treat that as a multi-layer perceptron afterwards. So this can so this fully connected layer, it can we can like put it after all the convolutions are done, because output of the fully connected layer does not store any local information. Because fully connected layer, they are connected. So each neuron is connected to in the input is connected to all the neurons in the output. But convolutions, they store local information very well. So performing a convolution on the output of a fully connected layer will be meaningless. Now we have global average pooling. In this previous slide, we concatenated all the feature map. Instead of that, we can also take the average of each map and consider that as like one neuron. Usually you don't do that because this gives better results. But this also, like taking average of each filter, can only be done after you have finished all the convolution operation and you want to like use the fully connected layers. Yes.
So in that one they did 6 by 6. Like it looked like they were using a window in the pool.
Yes, so they used average pooling there. This is global average pooling where each filter will have like one number, but you can also stride along these to actually get like some more information. So if this is like let's say 10 cross 10 and you have 6 cross 6, then you can convolve, like find average for each stride and then concatenate them and pass.
It's just taking an average over whatever that is.
Yeah, average over, yeah. So whatever your kernel size is, you just put that on the image, and for that like segment you take the average. So now let's talk about deep residual networks. So a deep convolutional neural network would perform convolutions after convolution after convolution. So deep residual network, or ResNet, it has like given state-of-the-art result for image classification, and what it does is, so I'll first like explain the motivation behind this ResNet. So when you have, let's say you have 100-layer CNN. So as you approach to the end layers, we usually face the gradient vanishing problem, because the gradients they are just like too low, and like they are getting multiplied, and usually you face the gradient vanishing problem. So Microsoft came up with deep residual networks, where I'll show in the next slide how, like here, when you have some input, you pass it through a small CNN, and you connect the input with the output and you add it, and these you'll have like 152 layers of the same thing. So what you're actually trying to do is, if a layer is, if this model is not learning anything, then instead of like going through this, you just like have a residue. And let me just go over. So when you have a very large CNN, we end up forcing many of the layers to do nothing on the input. Until then, we will suffer from like vanishing gradient problem. So the output of an early layer gets garbled by untrained later layers, or a small change in the output of an early layer will not probably change any output meaningfully. So if you make any small change here, like in, let's say, input layer or the first previous layer, the output in the last layers, they won't change much because of the convolutions and the max pooling, whatever we are using. And even if it did, the effects of small change are likely quite chaotic and unpredictable. Like we won't be able to predict what these small changes are doing. So what ResNets are, connecting this input and like passing it after each so after like 2 layers, we connect the input back. Then we'll have the same thing, and the input will be connected back. Do we have? Wait. You're showing? Yeah, I'll just. If you can see here, the last line. So yeah, the input gets transferred back. So if it's important, that it will learn, and we'll like learn more about it in the next half. So let's look at some like visualizations. So AlexNet is another like convolutional neural network, and so if you can see the first half, it's actually learning some kind of edges, and it's not learning like which color it is. It's just like trying to learn some kind of. So this thing is learning some kind of blob. There are some edges you can see. And in the bottom half, it's actually trying to learn the colors along with the colors and not just like grayscale edge detectors. So like when you have like multiple channels, like if you want to like see how, so this for example is trying to learn some kind of purple blob, or like there you can have it's trying to learn some kind of red edge. So this is how the CNN like filters, like this is what each filter is learning, and this is like what like you see when you visualize a filter.
So that's in a single layer, correct? These are all the filters in a single layer?
No, actually we've just picked like this are just like picked from this does not necessarily have to be from single layer, like this like
it's a layer out of a multi-layer convolution, correct?
no, these are like each filter.
Yeah,
Then
for this is the first layer of AlexNet. So AlexNet started off with like really large convolutions at the start. So they had like 11 by 11 filters. So you can easily visualize them like this. Just plot them like that.
so we can also look at the activation maps. So as you can see that like you're not able to see much because like they're not actually learning anything. So they are what we call as dead filters. So dead filters, that they can happen when you have high learning rate, so you overshot and you're not able to learn anything. And so this can also happen when all your like the dot product that you're getting like is negative for many of the like for a whole segment, and when you have passed it through a ReLU activation, it becomes 0, and after that like it's not able to learn anything. So when such case happens, you get dead filters again. And one thing that we need to like know like understand is all the feature maps, they should be uncorrelated. That means that all the feature maps, they're trying to learn something, right? Some kind of like edge or blob. They should be uncorrelated so that they learn different things. If they're correlated, then they'll just be learning the same thing. Okay, so let's try to understand what the CNNs have learned. So if you cover up some part of the picture, So first, this is like a Pomeranian, right? And when you can like cover some part of the picture and different parts. When you have covered the different parts, we record the probability of the true class, right? So we cover up some part, pass it through the model, and see what it is trying to predict. Is it like still predicting the true class or not? So when we do that a lot, we can see this visualization where these blue parts, they represent that the probability drops sharply when those parts are hidden. So that part of the image is actually very important for making the prediction. So so here it's when it comes to like predicting the Pomeranian, this part is like very important. When you want to predict the car wheel, the CNN is actually understand that this part is very important. And when the CNN wants to detect an Afghan hound, so CNN has already understood that this part is very important, because whenever that part was covered, the probability of like predicting that this image is an Afghan hound dropped sharply. So now Soham will give you some like practical demo.
Okay, let me. Hey, give my charger now. मिरर कैसे करता Oh shit. What? Okay, no, I'm what is Come on. Sorry. Are you? Okay. Okay. So this part of the recitation is going to cover how do we do CNNs in PyTorch. It's I mean the same principles you can still apply in TensorFlow, just that like it's just different frameworks. That's all. So let me zoom into this a bit. Yeah. What is happening? Okay. Okay. So first we'll start off with the usual imports that we have. We'll have torch.nn.functional. So so in functional, you basically build your own. You apply either the convolutional directly or the dropout directly and stuff. You want autograd because you want autograd.variable. You want nn.modules. NumPy, you want to plot stuff. And torch vision is another very useful repository for doing CNNs and PyTorch, because you're usually always dealing with image data. So it gives you this interesting thing called transforms, which lets you take a data loader and put a couple of compose a couple of transforms sequentially. So it could maybe do a resizing, cropping of the image, adding random noise, normalizing. So all the stuff that you're doing in your current homework, you could do that in like one class using transforms. And datasets is basically a dataset loader kind of thing. So I'm going to go fairly quickly through the actual through these parts of PyTorch. So if I'm going too fast, just stop me, because I want to get to a little more complicated stuff like, oh, okay, how do we build a ResNet and stuff? Yeah.
Could you please zoom in a little bit?
Sorry?
Zoom in.
Zoom in. Okay. Is this better?
Yeah, good.
Okay. Okay. So let's first talk about. We always want to figure out what's the size of the tensors that we want to give to our model that we want to build. So let's say we have 2D images, 2D data like images, and usually we won't be working with 3D data, so that's fine. So 2D data will look, each sample will look like a number of channels, height and width. So let's say you're dealing with MNIST data, which is black and white. Channels, number of channels will just be 1, but and height and width will be 28. But if you're dealing with CFAR, I think it's 32, is it? Roof. CFAR is how much? 64 or 32?
64.
64. So and 3 channels, because red, blue, and green. And usually always your first dimension is the number of samples. Similarly, 1D data like stock prices and also MFCC coefficients. So let's say homework 2 part 2, you'll be dealing with audio data. And these are 1D data that have a number of features at each time step, and it goes through time. So you have number of samples, which is maybe one sample is one utterance, or a couple of frames in one utterance, and number of frequency bands. Let's say homework 1 data will be 40, and time is how long that utterance is. So so based on that, what should our filters look like? So 2D filters should look like the couple of things that you need to specify is the number of output channels, number of input channels, and the height and width of the filters. So usually in these are the sizes that you'll require. So let's say you're dealing with a 32 by 32 image. You would want something like this. One number of samples is 1, 3 channels, 32 by 32. And similarly, let's say you have a 40-dimensional signal. You would want and you have 1 sample. You have 40-dimensional and 100 time steps. So that looks like this. So let's talk about what the next thing that you're going to do. You're going to load the data and you're going to transform it. So Torch Vision gives you a really nice API to do this. What you have is all these classes under Torch Vision transforms, like random resize crop, random horizontal flip, color jitter, and these are all important things that you will pre-processing steps that you will see in CNN papers. Especially color jitter, it works well for generalization, basically not overfitting. So what you can do is, let's say I specify this data transform that I'm composing sequentially. First, I'm going to get a random resized crop of that image. So often, let's say you're dealing with large images which are maybe of size 320 by 240. But you want to crop maybe a random part of it and resize that to 100. So you can specify that in this class. You can randomly choose to flip that image horizontally, and then you convert it. So the important thing is, the last thing you need is the .2 tensor function. So the .2 tensor makes it a torch tensor and makes it a variable, so that you can directly use that in your data. So and this is another important thing. Let's say you're dealing with ImageNet data. You would want to normalize your data. So remember in homework 2 part 1, what you're doing is ZCA whitening. So this is kind of something like that, just that you know these are already computed for you, the means and standard deviations for each channel. So you want to remove the mean, you want to remove the, you want to scale by the standard deviation so that it's a standard normal distribution kind of thing. So and that you would want to put in after 2 tensor. So there are a couple of things. Usually the image stuff that you work with, like cropping, resizing and stuff, is before .2 tensor, and everything like normalizing and all these things you can put after 2 tensor. And you can make your own transforms as well. So let's say I wanted to make my own ZCA transform. I can specify something like this. I have a class. All you need to do is, so this part is not important, the representation. That's just for printing and stuff. So ZCA, you remember that you first need to remove the mean, and you also need to record the principal components. So let's say my principal components are P. So I just record that here. And obviously, I can't give you the implementation now because that's part of homework 2 part 1. So you can implement your transform here, and you can use it straight away in your composed transform object. Next, how do we use this in a pipeline? So you work with data loaders in homework 1 part 2. You have PyTorch also gives you easy ways to load image data. So let's say you have all your image data in one folder, and for me I have all of it in this folder, so I have just 2 images. So what I'm going to do is I'm going to say that my image folder root is dot, which is the current folder that I'm in. So what PyTorch does is that you specify the root folder, and that can have multiple folders within it containing images. So you can so this is going to discover that, oh, okay, you know, image folder has a couple of images. Let me load stuff from there. So I'm going to create a data loader that takes this data set. For this, another thing I missed is, for this data set, I specified that I'm going to load from this root, and also I'm going to apply this transform. So that this transform was random resize crop, random horizontal flip, and .2 tensor. Yeah, and then I can wrap it inside a data loader, and I can use it straight away. Then it becomes a for x comma y in dataset loader. And in our case, we don't have any labels yet, so I'm ignoring that part. But y is usually inferred from the folder that your image is in. So so you can see that if I let me just. I need to run these parts as well. So I have 2 images. Let me actually maybe show you the images that I have. So this is an owl, and this is an image of a guy running. Okay. So so you see what it's doing, right? It's randomly cropping the image somewhere, but it's also giving me a size of 100 by 100. So so this is, let's say this is exactly what I want. Then I can use this data loader directly. So now moving on to how do you actually specify a convolutional model. So there are a couple of things. Most important for us will be conv 2D, max pool 2D, and average pool 2D. So this is something that you would use in deconvolutional layers, which we are not covering, so I'm going to skip that. So again, like how you specified linear networks in PyTorch is you did nn.linear. So similarly, to create CNNs, what you can do is you can specify torch.nn.conv2d. And remember the couple of things that we wanted to specify: number of input channels, number of output channels, the height and width of the filter, and usually height and width of the filter is the same. So that is specified by kernel size. So kernel size 5 means the filter is 5 by 5. Stride of 1 and padding of 2. So these are still I think optional things that you can put in. These are, as far as I know, they're compulsory. You can't skip any of these. So I think if you don't give anything, stride is default 1 and padding is default 0. And if I want an average pooling layer, then I just specify layer average and what's the kernel size that I want to pool over. So 32 by 32 means that that's a huge size. Let's make it 3. So what it'll do is over the filter, then it'll in a 3 by 3 area, then it'll take an average pool of that and it'll output one value. So actually, usually people do 2. So if you do 2, that means you're downsampling by a factor of half. You're making, if you have 40, then you're becoming your filter, your next layer inputs are becoming size 20. Okay. So let's say I have this. My input image. Okay, I forgot what my input image size was. Let's print my input image size. Okay, so my input image size was 32, and I had 20 channels. So that's why you see the output that's coming out of here, the Y. It will have 20 channels here. I have only one sample. And because I put a padding of 2 for a kernel size of 5, and if you work this out, you'll see why. Should I show them the working? You covered it, right?
Yeah, actually, I think it was covered. Right, so.
Yeah, okay. So, so you'll see why for kernel size, right, yes.
Can you just review the formula?
Right, I don't know what the actual formula is, but this is how I think about it. So you have an image here. So your, let's say your kernel size is 5, right? So that's, let's say for when it's centered about here, for you to not lose any input size, you would want 1, 2, 3, 4, 5. So that's why if you visualize this, then you'll know that, okay, I need a padding size of 2 if I have a kernel size of 5. So it's, I think, like you can take 2 times, padding should be the kernel size minus 1 by 2 if you want the same thing. So.
And if you want the formula for
yeah,
the
what's
resulting, like,
yeah.
Yeah, but this is correct.
Yeah. This. Okay. Right. So now the thing is, I can still, I don't need to specify layer by layer. Okay, conv 1, conv 2, and in my forward say, okay, do conv 1 of x, conv 2 of x. So one thing that I really suggest you guys using is sequential. In my office hours, I didn't see a lot of people using it. So, but it really makes life a lot easier, and you'll see why when I get to ResNets. So, so if I do nn.sequential, what it's doing is first it's going to do, first it's doing a layer average. Why am I doing a layer average first? That is not correct. Oops. Huh. All right. You need a star here. Right. So remember what we said. First you go through the CNN. You have 20 filters, and then you had 1 by 20 by 32 by 32. But then you're doing average pooling, and with a kernel size of 2, then you'll have 16 by 16 output in the end. Can anyone say what would happen if I use a kernel size of 32? Yeah, correct. So okay, this part I'm going to skip. This is more like, so let's say you don't want to actually specify for some reason use the nn.com2d wrapper kind of thing. What you can do is you have all these low-level functions. So that's under torch.nn.functional. So what you need to do is, let's say you want to apply a convolution. you can specify the image. You also need to specify the parameters, the filters yourself. So this part is a little tricky. So I usually never use this, at least for convolution. I use it usually for dropouts and stuff, because sometimes it just makes things easier than to declare everything in the model. So padding. So here you can see how padding affects the final size of your after one layer. So again, we are keeping everything constant, just changing the padding. So let's say padding was 0, and now the kernel size is 7, right? So 7 minus 1 by 2 is 3. So that means that you would need a padding of 3 here to have the same size. And I think you would probably see that in here. See, 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Yeah, this is the one. So that gives you the same size. And sometimes you might want to, if you're dealing with, let's say, not square images, and this usually happens sometimes in self-driving cars and stuff. You might want to have different paddings for different dimensions, and you can specify that using this. So if I used no padding in my first dimension, so then it becomes a 26 here. But if I specify 3 in the other one, then it still stays 32. So depending on your application, you would want to use different kinds of padding. Okay. I'm going to skip this part. Okay, now what else is important? You want to have batch norm, and you want to have dropout because you want to not overfit and still make large models. So how do you do that? You guys did, I think, like for good performing models in homework 1 part 2, most probably you guys had to use batch norm. So that was just a nn.batch norm layer. But in this case, you need to do it on a 2D level. So that's a different class. That's batch norm 2D. And similarly for dropout, it's dropout 2D. So essentially, almost everything you can just apply a 2D, and it probably exists for CNNs. And similarly, we already kind of went through downsampling. You can do that using max pool 2D and average pool 2D in this manner. Yeah. Yeah. Sorry.
Question about dropout 2D.
Mm-hmm.
In the homework, in one of the signatures for the function, saying we'll use nn.dropout.
Mm-hmm.
Do you always use dropout 2D in your models, or can you use dropout as well? What's the difference between the two in terms of, like, one's looking at a different set of dimensions, but if you use just a normal dropout and it's somehow coercing the 2 dimensions into one, is it doing kind of the same thing, or
So,
do you use 2D?
Functionally, there shouldn't be any difference between.
Dropout 2D zeros whole channels.
It does?
Yeah, and like
Oh,
it's
okay.
like it's gonna take one of your channels and make it only full of zeros. You can still use dropout, and it works like regular dropout. It just cancels some zeros.
But like if I'm dealing with 96 channels from like a previous filter to do a dropout, some of those can be still active after a dropout. Like one channel isn't getting completely dropped out.
If you use
Whereas
regular
2D
dropouts, it won't count. That still makes sense. I think you can do both.
Yeah,
I mean,
yeah.
They have different effects. But
Yeah,
you
yeah.
can-
People do both, like, I think.
Okay.
Yeah. Downsampling we went through. Max pooling, average pooling, and strided convolutions also pretty standard. So I mean, I'm not sure, like, if I should actually go into detail into this, or I can skip to the more complicated stuff. Upsampling is something that you might require for, let's say, an application like semantic segmentation, or basically in deconvolution layers. But again, we are not covering most of that, and it's not relevant to the homeworks that we are doing currently. So I'm going to skip. So if you want to read image data and display it and stuff, and basically for yourself to know how things are working, a good library to do that is under skimage, you have IO, and you can do io.imread. There's also OpenCV, but installing OpenCV can sometimes be a pain, especially if you're on Windows. There's also PIL, which is the image pillow library, and I think skimage is an abstraction on top of pillow. But anyways, so what you can always do is you can do an imread, and you can do a plt.imshow to actually see the image. So here we are. So these are yeah. So pillow is the second kind of way of doing things. So let's. So here. These are two just different ways of loading images and showing them. So okay, now this part I want to talk about is how you can use pre-trained models in PyTorch. So this is not something that you would find very useful for your homeworks, but it's something that you would find very useful for your projects. So let's say we have usually now people are working on a lot of complicated tasks like visual question answering, image captioning, and the problem with this is that you already have a complicated architecture on top of the image features that you extract. So if you have this bigger model, usually feature extraction itself, learning good features takes a lot of good examples. So what people do is usually use pre-trained models trained on ImageNet and use the features layer from that. So let's say, for example, I'm using VGG. So how I would do that's one of the architecture, one of the famous working architecture. So let's say, and these are all provided in Torch Vision. So Torch Vision is awesome. So all I need to do is get VGG16 equals to models of VGG16, and I need to specify pre-trained equals to true if I don't want random weights. So if you guys do this on your laptops, you'll first see that it's downloading these weights first because it has never downloaded it before. You can do this download yourself and copy them into the respective paths that are required, or you could just use this. So let's say, so VGG model looks something like this. There are two parts. One is the feature extractor part, which is mostly just convolutions followed by values and pooling layers. And remember, this VGG16, so like version 16. So this is pretty. This doesn't do a lot of things like use batch norm and stuff, whereas VGG19 does, I think. And then parts of classifier part. So if you see here. Well, if you look at the output from here, from this part of the network, it will be 7 by 7 by 512. So you have 512 filters here, and the last outputs will be 7 by 7. So if you flatten that, you will have 25088 features. So that's why if you see here the sequential. In the sequential, the first linear layer is number of in features is 25088. Then you have 4096, 4096, 4096, and then finally 1000 classes, which is the number of classes for ImageNet. But let's say you want to use the feature extractor. You want the 4096 vectors and sized vectors, and these are actually very useful for the tasks that we have, like VQN, image captioning, and stuff. So what you do is, let's say I only want the convolutional features, then I could just take VGG feature extractor as VGG16.features. So that will just take this part of the model, right? And then I can apply that to, and in VGG you usually use 224 by 224 images. ImageNet is 224 by 224. So once you apply the feature extractor, then you will see that, like I said, you have 512 channels, 7 by 7. If I if I can do this to flatten an image, flatten the other dimensions. So I have only one example, so 512 by 7 by 7 becomes 25088. But let's say I also want to, I want to get instead the 4096 size vector. So for that, what I would need to do is, I need to remove basically this layer, these parts. Okay, so that is done easily. So this is a sequential thing, right? So what I can do is, I can say the new classifier is another sequential, and I take the, sorry, okay, let me just say, so I'm taking this, I'm instantiating another model of VGG16. I'm taking its classifier, I'm taking its children. So children means the list of things I have in here, and I want to remove just the last layer. So I think this still includes the dropout, and I want to convert that into a list. And you remember, you always need to put this star in front, so that, like, just for PyTorch semantics, because it kind of expands the layer into arguments. So then I can do an nn.sequential, and that's my new classifier without the last layer. So then I can replace the classifier in here, and I say, okay, VGG16 4096 classifier equals to new classifier. And once I do that, I can pass in that same image again, and I'll get a 4096 size vector. So this is how you can get it to be the before the classification layer, if you want to just use the features. Similarly, you can do that for ResNet as well. And there are a lot of these. You have Inception Net, you have Squeeze Net. Almost every famous architecture that works well on ImageNet is there on Torch Vision. And again, for that same thing, see exactly what I'm doing is, ResNet is just sequential, so I can take resnet.children, remove the last layer, and do an nn.sequential on the modules. And when I do that, I get something of this size. Okay, so this part, okay. Do you guys want me to go through how to debug CNNs or how to build, let's say, ResNet or InceptionNet? Because this code will be there. Whatever you want me to go through, I'll go through now.
So sorry, what were you talking?
Debugging CNNs or how to build popular ResNets and InceptionNet and architectures like these yourself.
So like in terms of our homework part 2, I haven't read it yet. Are we going to be building all these popular architectures in our part 2?
Part 2 is audio data, so you won't be using these stuff. But actually, no, it will help. Yeah, you can use these ideas in homework 2, part 2. Okay, I'll go through this. So Dhruv went through the ResNet architecture. So essentially what it is if you look at the picture here, it's pretty scary, right? It's just a whole bunch of layers, and remember why I said sequential is important. So you can always have a list and then do nn.sequential, and everything works fine. Your forward is much easier to implement in PyTorch. So what's the basic building block in a ResNet? It consists of 2 convolution layers with activations, and also this residual connection that you have, which is just adding the plus the identity of the input. So for the ResNet building block, what I'm going to do is, oh shoot, I don't have a part here. So let's say I specify this function conf3x3. So what I want to do here is in planes, and stride. So what I can do here is return convolutional layer, and I say that, okay, I have inputs. I might be getting some of the signatures wrong. I'll update this before I uploaded. I want outputs equals number of output filters is this. I want my stride to be this, and so on. So what this will do is return you one convolutional layer, right? So if you can see here in this code, what you can have is the first convolution, you'll have another batch norm after that, because ResNet strongly uses a lot of batch norms. Then you will have your activation, then a second convolutional layer, batch norm. If you want to do downsampling, you can do downsampling, but I'm not doing any of this here, so I'm going to remove that, and whatever stride you want. So what you need to do, ResNets are pretty easy to do. So what you can do is you just do forward in your forward. You compute, okay, my residual is X, which is the input that came in. So my residual is this. This is my residual. Okay, and then I can one by one apply all these functions. Convolutional batch norm ReLU, convolution batch norm, and then after that I can add in the residual, and after that I apply the ReLU. So how do I use this? I could pretty much do something like ResNet model equals to nn.sequential. All I need to do is ResNet. I can create a list of these building blocks based on the so for and I could have my list of parameters here. I don't have it here, but so what this will do is just create a sequential module, and you can use this straight away. This makes your code a lot, just 31 lines, while the model itself is actually pretty complex. Similarly, another popular architecture is InceptionNet, which looks a lot like this, even more complicated. So in InceptionNet, the main building blocks, if you see, are you'll have multiple branches, you'll have convolutional blocks. These are each of this is a convolutional block consisting of a convolution, batch norm, and ReLU activation. You have one by one convolution. So the one by one convolution, you would think, why is that helpful in any way? So if you think about it, one by one convolution is just like at a scalar value at each position and just multiplying it together. So, but remember, if you have, let's say, 320 channels in the previous input, in the next layer you have 20 channels, but one by one convolution, you're essentially doing dimensionality reduction by doing a weighted sum of all your previous channels, if you're doing one by one. So that was the main reason that InceptionNet came up with this approach. And then what you do is you concatenate filters in the end. So what I would say is, if you're building complex models, it always helps to break down a model into its subunits and implement them out. So similarly in here, I don't know, how long do I have? 5 minutes, right? So so what you do is you specify each branch. So let's say this is my one by one branch. Okay, this is my one by one branch. My 5 by 5 branch is here. For that, I'll have one convolutional with kernel size 1, because I have one by one convolution, and then another one with kernel size 5. So that's this one. So that's this branch for me. Branch pool is this one. So first I do kernel size, this should be 3. Huh. Okay, I'm missing something here. There should be a pooling layer here, which I'm missing. But anyways, and the last 3 by 3 one is again pretty similar to what you're doing here, just that you have 1 by 1 and first kernel size 1, then kernel size 3. And you could actually remove this one. Anyways, and finally what you do is, the reason that I don't need to have an explicit pooling layer here is I'm using the functional torch.nn.functional thing here. So I can do f.average pool 2D of an input and specify the kernel size. So I compute these branches 1 by 1, and then in the end I take all the outputs, which are the outputs from each branch, and what I want to do is concatenate them across the filter dimension. So remember that in 2D data we are always dealing with number of samples, number of filters, height, and width. So if you're concatenating across dimension 1, which is the second dimension, you're concatenating all the filters together. So that's the main thing, how you build all these architectures. The one thing I wanted to say about debugging CNNs is that I think Dhruv covered part of it. If your learning rate is too high, you're going to see a lot of dead filters, which is for most of your inputs, most of the channels are always black. So this is still fine. It's a couple of them are active. And secondly, another important thing is that your feature maps should be more or less uncorrelated. So this is, I mean, you could come up with a measure for it, but people don't, I'm not sure if people actually do that, but what you can do is just look at these things, and usually if you're this is a pre-trained model, so it works well. But if it's a bad model that hasn't been trained well, then you'll see that most of the outputs from this layer will look almost the same. So they look very correlated, which means that essentially a lot of your filters are redundant because they are outputting the same thing, and you're not learning anything new. So these are, I guess, two easy ways to debug CNNs when you're working with them.
So how do you get this image?
Right. So yeah, I didn't get the time to go through that. So what I do is I take the features until VG16.features until a certain layer, and I'm passing that through. I'm taking this and I'm putting inputs into it, and what's coming out is something, let's say, number of samples times number of filters times height times width, right? And then you can use this thing called torchvision.utils.makeGrid, and I'm using that in here. So I essentially, so you can specify all these things here, like how many rows you want, do you want to scale each, do you want to normalize each, how much space you want in between each cell in this grid. And then this creates an image that you can use plt.show to imshow to show that image in Jupyter Notebook. So essentially, this creates an image out of many images. You pass it a torch tensor essentially, and then plt.imshow actually shows it in here.
So we feed in observations.
Yeah.
To the net, and we kind of get it doing some stuff, and then we can see what's.
Yeah, because I mean, you will. It's more qualitative than quantitative, but often that helps. Like if you use too high a learning rate, you're going to see a lot of dead filters. So that's one easy way to debug CNNs, I think. Yeah, I'm out of time. Any questions?
So when you say debug, when you see correlated filters, what do you do? Do you reduce the size of the?
Yeah. You can start reducing. Yeah, essentially. You want to reduce the model capacity and get to the point that your features are not uncorrelated and are not correlated, and you're maybe doing some underfitting. So once you do that, then you can be like, okay, now I can slowly increase my capacity. Let's see, should I add more layers? Should I add more filters at the top, or should I add more filters towards the end? Usually, you add more filters at the start, I think. Yeah. Any more questions? Okay.